Hey, Alex. So I've been reading about this Impact Quantum podcast topic, and it talks about quantum chemistry and computing really shaking things up. But, like, why? What are the traditional methods not getting right?
Oh, Heidi, great question. Yeah, it's pretty wild. See, traditional computational methods, like, things like DFT or coupled cluster, they're approximations, right? And they really struggle with what we call strongly correlated electrons. These are electrons that their interactions are just too complex for those simpler one electron theories to accurately describe. We're talking about things like Mott insulating states or even like weird superconductivity.
Strongly correlated electrons. That sounds super specific. So these are like what, in certain materials?
Exactly. Often in systems with incompletely filled d or f electron shells, narrow energy bands. It's especially tricky when you're looking at transition metals, like in enzyme active sites or even exotic catalysts like iron sulfur clusters. Classical models, they can underestimate the number of electronic states in these FS clusters by orders of magnitude. It's a huge blind spot, really. Quantum computing, though, it processes quantum behavior natively. It's not trying to like mimic it with classical bits, so it can actually describe electron entanglement and all that probabilistic behavior accurately.
Wow, so it's a fundamental shift in how we approach these problems. But okay, is any of this actually happening now? I mean, are these quantum computers already making a difference in chemistry like today?
Totally. That's the exciting part. Even noisy intermediate scale quantum or NISQ hardware, which isn't fault tolerant yet, it's showing massive promise. Like in catalyst design for green chemistry, we're using quantum mechanics to simulate how catalysts interact with reactants, helping us design more efficient ones. And drug discovery? Huge. Quantum chemistry predicts molecular structures and properties, which means faster identification of drug candidates. Pharma companies are already collaborating to find novel antibiotics and even refine clinical trials. We're also seeing hybrid quantum classical workflows for robust drug design.
No way. Drug discovery already? And what about materials like for solar cells or something?
Absolutely, Heidi. Materials for extreme conditions, too. Quantum chemistry lets us study electronic structures and optical characteristics, which is key for developing new solar cells, batteries, even magnets. Researchers are modeling complex systems classical computers can't handle. And we've had some cool early wins. Harvard trapped molecules for quantum operations. Google in 2025 reported a quantum computer was 13,000 times faster for a specific molecular calculation. IBM's even aiming for quantum advantage by 2026. It's like really happening.
That's just mind-blowing for chemistry and materials. But the prompt mentioned high energy physics too. That seems like a totally different beast. How does quantum computing fit into like simulating the Big Bang?
Oh, that's where it gets really cosmic, Heidi. High energy physics, like simulating particle interactions right after the Big Bang, those are immense computational challenges for classical supercomputers, especially when you're dealing with non perturbative effects and quantum chromodynamics, or QCD. Classical machines they really struggle there.
QCD, is that like what quarks are doing?
Exactly. Quarks and gluons. The thing is, quantum systems are uniquely suited for high energy physics because they can directly encode gauge symmetries, and that's absolutely critical for simulating phenomena like quark gluon plasmas, that state of matter right after the universe began. Researchers are actively developing quantum algorithms, even for fluid flows, that could be extended to simulate these plasmas. We've even seen proof of principle simulations on NISQ devices, showing it's actually feasible to simulate open quantum systems relevant to heavy ion collisions and quark-gluon plasma studies. The potential, it's just enormous to unlock physics we currently can't even touch with classical computers, totally reshaping our understanding of strong interactions. It's wild.